All right, back from break. Here is that second set of problems. So here is another midterm. I know it looks like the other midterm we just looked at, but these are different problems now. Again, it's a midterm from several years ago, and we're going to start out looking at charged particles, ions, doubly charged helium atoms, being accelerated through an electric field and then being directed in a magnetic field. So let's see how that works. So we've got these helium nuclei, really, because they're doubly charged. Let's see. And we're looking at two different isotopes. And so here is the helium-3 isotope, and here is the helium-4. And the helium-3 comes in at 3.0160. I didn't subtract off any electron masses. I guess, strictly speaking, I should have. It turns out the electron masses are so small, they're like 0.0005, but they would show up in these last digits. So for our level of, if we're keeping 3 significant figures, the electron masses aren't going to be important. But I did look up and write down the masses for these isotopes just to start getting some familiarity with that, because later in the course we're going to be looking more and more at nuclear physics, and we're going to be looking at different isotopes, and we're going to need to be thinking in terms of individual masses, and we need to do that here also. So the masses here are going to make a difference. So I want to keep track of these masses, but you can see to 3 significant figures, helium-4 is 4.00. Helium-3, there's a few isotopes early in the periodic table, isotopes of hydrogen and helium, where that third digit makes a difference, so 3.01. Anyway, I wrote down that 1 gram is the equivalent of 6.022 10 to the 23rd. That's an atomic mass unit. So we have started using, in some of these examples, atomic mass units to keep track of looking up the masses of some of these things. And then, so 1 gram is the equivalent of Avogadro's number of atomic mass units. That's how atomic mass units in grams are defined. And so what we want to be able to do is get the mass of an individual, just one helium nucleus or one helium-4 nucleus, helium-3, helium-4, and convert that into kilograms. So 1 kilogram is the same thing as Avogadro's number times 1,000 of atomic mass units. So that's a kilomole instead of just a mole. So anyway, those are good conversion factors to start working from. And I know there's other conversion factors introduced, kind of the inverse of this. Either way is fine, but a recognition that this is just Avogadro's number, that might be useful to think about. So anyway, in this problem, what we're going to do is we're going to use an electric field to accelerate helium nuclei. The electrons have been removed. It's doubly charged. And so we're going to use an electric field to speed them up, and then they're going to enter a magnetic field region. So here is the magnetic field region, and what's going to happen is, what we've shown is that a charged particle moving through a magnetic field will follow a curved path. If the magnetic field is uniform, that path will be circular, or a spiral, with a fixed value of r. So let's start writing down some stuff for circular motion. So the circular motion formula is A is to V is V is to R. So A is equal to V squared over R. And then the acceleration of the charged particle is given by a force divided by its mass. The force acting on one of these charged particles in a magnetic field will be given by QVB. So that's QVB divided by M. I can take the kinematic formula, A is to V is V is to R, and set that equal to QVB over M. And what that leads us to, we've derived this already, is that we have a radius of the circular motion of a charged particle in a magnetic field given by mv over qb. So if the particle's just sitting there at rest, not much is going to happen. But if it's in motion, then it will follow a circular path given by mv over qb. Now, the kinetic energy that the particle is going to come in with, notice this is in terms of 1700 volts. So if I'm accelerating this using 1700 volts, what we can do is take the charge of the helium nuclei coming in. Now, whether it's helium-3 or helium-4, they're both doubly charged. And so both electrons have been removed. Helium is element number 2. Both electrons have been removed. And so I'm going to get 2 times the fundamental charge. So I've got 2 protons, that's their charge, multiplied by a voltage. Now this is in coulombs, this is in volts. That will give us joules. So I can calculate the kinetic energy if I know the voltages used in accelerating the charges. I need to know how much charge they had and what the voltage was. This is doubly charged, so it's got that extra factor of 2, but it's going to end up with these individual helium-3, helium-4 nuclei will have kinetic energies of 5.44, 10 to the minus 16 joules. Now, as we saw before, earlier in the course, I guess, the kinetic energy is 1/2 mv squared. V is given by 2 times the kinetic energy. I got to remember the square root on that. Now the masses here, this is where we don't want to get tripped up. The masses for the helium-3 and the helium-4 were given. Again, I did not account for the electrons, but I don't think that's going to cause a problem. So to 3 significant figures, the helium-3, helium-4 masses convert out to be 5.01 and 6.65 times 10 to the minus 27 kilograms. So again, when we're doing these individual atoms or individual nuclei problems, the masses are going to be tiny, right? And the energies are going to be tiny. So I've got to pay attention to my scientific notation. So plugging into the formula, I got that the helium-3s and helium-4s, their velocities are 466,000 meters per second, or 404,000 meters per second for the helium-4. So those are the differences in the speeds of these 2 different isotopes of helium. That means that the radius of curvature is going to be different for the 2 different isotopes. When I use mv over qb, the q here is, once again, it's 2 times the fundamental charge. So that's 3.2 10 to the minus 19 coulombs. The magnetic field, we are told, is 0.340 Tesla. The radius of curvature I get for the helium is helium-3 is 2.15 centimeters. For the helium-4 is 2.47. Okay. This is a mass spectrometer. So what we're doing is we're sending through a mixed set of isotopes. We're sending a mixed set of isotopes in, and we're using the properties of the trajectories in a magnetic field. We're using the differences in mass to separate out the helium-3 and the helium-4 isotopes. So they're going to land at different locations. If we have a detector here, we can determine how many helium-3s we have and how many helium-4s. If there's some way to collect them, we've actually separated the 2 isotopes using a magnetic field to do that. So this is an interesting problem with you know, some real practical applications for sorting out different sorts of materials, or just finding out what the masses of different materials are. Questions on any of that? Moving on to the next problem here. So problem 2 is actually, so if I had to identify a chapter, I would say this is mostly due to chapter 27. Again, it's good to have, you guys have this background in 27, 28, 29, all of this magnetic force and field stuff that's all interconnected. But you know, this is kind of like a chapter 20, this is like a chapter 28 problem. And so here what we're looking at is we've got 4 different wires. Now these wires are arranged in a square configuration. That sounds a little weird. Each one has a current of 2 amps and they're all moving in the same direction. Distance between the wires is 5 centimeters. So what's happening is that the wires, the currents, this was like a homework problem, the currents are moving out of the page. So the currents are coming out of the page towards us. I should really say that more specifically, huh? Okay. In my diagram, I've identified it that way. So I've assumed that the currents are coming out towards us. Now, if you remember, if we look at a wire, it's going to have a magnetic field that forms the magnetic fields are going to be right-handed loops surrounding the wire. And so what we can do is, if I've got a point right here, and I'm asking, what's the contribution of the magnetic field due to the presence of current number 1, well, I can come out from current 1 to that point, and then I turn 90 degrees. Because I'm looking at this picture and thinking if I start here and come out some distance, the magnetic field is going to be directed perpendicular to that radius. So if I think of that as a radius, some value of r moving away from the center of the wire, not the surface, but the center. And then we're going to have a magnetic field that is directed here. And so that's what's happening at this location. So here what I'm doing is I'm coming at a 45-degree angle. The magnetic field is going to be tipped 90 degrees, and so the magnetic field contribution from current 1 would be in that direction. And then if I move on to current number 2 and do the same thing, it's going to be off in this direction. Current 3 is here and current 4 is here. So go through, check, make sure that you understand how we're determining these magnetic field directions from these, stop by if you guys have questions on this. It's something we've looked at. It is tricky. But what's happening here is that the contributions from from current 1 and current 3 are exactly opposed. And then 2 and 4 also are exactly opposed. And so they're going to cancel out. The magnetic field is going to be 0. Let's see. Yeah, what's the magnetic field at 2 different locations? So going back, they first of all ask about a center location. Now there's enough symmetry here, I'm thinking either the effects of the wires all add together to something, maybe I have to multiply by 4, or they could cancel out. Magnetic fields are vectors, and so the direction is going to make a difference. And that's what happened in this case. Now we've seen some examples like this in other parts of the course where we have electric fields or that cancel out. If you're going to say on a problem that fields cancel out to 0, you've got to show enough diagrams or show enough work or write down an explanation as to why they're canceling out. You can't, you can just write the B field at point A is 0, but you won't get credit, okay? Or you'll get very little credit for saying that. So what you want to be able to do is, on a problem like A, you do have to show some diagrams, enough diagrams, probably this would be enough, but to show that when you start adding together as vectors, these magnetic fields, that they all add up to be 0. Okay, so you do have to show that. You can't just write down 0 if you're expected to get full credit on these problems. In part B, we've now moved to a more difficult location to go in and determine the magnetic field. Now, once I finish part A, I am thinking, well, at point B, these two contributions should cancel. And so, did I actually point to that? I didn't. But let me say that here. So the contributions from what I've labeled as 1 and 4, 1 and 4 are going to be gone. So 1 and 4 are going to be opposing each other if I'm looking at point B. Now, what's going to be left are contributions from 2 and 3, and those are the ones that I've actually shown the diagram for. So what happens is, this is going to require a little bit of trigonometry probably, or geometry. I've got to be able to work around some triangles here. What I'm going to do is I'm going to determine a distance, and that's little r, and then I have to turn 90 degrees, and so here's what that looks like. And I don't know if I've drawn it. So let's take this triangle right here. The one that's coming from current number 3. What we've got here is this side is given as 5 centimeters. Now point B is halfway between, so that would be at 2.5 centimeters. And then the distance here I can get using Pythagorean's theorem. So from Pythagorean's theorem, the distance, little r, is 5.59 centimeters. Now I'm also going to need an angle. And so if I use the tangent of that angle, that would be 2.5 over 5, that would be 1/2. And the inverse tangent of that is 26.6. So I've got the little r value, which I'm going to need. This is my formula for the magnetic field surrounding a long wire of current. And that requires us to know how far we are from the wire. And it's going to require, let's see, when we start adding these vectors together, the magnetic field due to 3 is going to be tipped below the x-axis by theta, and the magnetic field from current 2 is going to be tipped upwards above. So if I take a look at these two magnetic fields, those have got to be added vectorially. Now, everybody, how many of you remember vector addition? Everybody, right? So what we can say then is I've got two vectors, magnetic field 2, magnetic field 3. They're the same magnitude. And I should have calculated that separately. I didn't. I kind of bundled it all together. But here's the formula, and it was given up here too. So they're the same magnitude because the currents are the same and the distances are the same. So that's good. These match up. And then they're tipped at the same angles. So the y components will cancel. Y components cancel out. And that says the net magnetic field will be in the negative x direction. And the component here is going to come from taking b cosine theta and b cosine theta. So I'm going to get 2 times b cosine thetas, and I plugged all that into one formula. Here is my factor of 2, here is the b field, here is the cosine theta. It worked out to be 12.8 microtesla. So a good example of determining how large the magnetic field might be, what we've learned in chapter 28, was whenever we have current running through a wire, we're going to have magnetic fields generated around that current. And here's an example of multiple currents, and then adding the magnetic fields together vectorially. Questions on any of that? So again, any questions on these, stop by. These are kind of our magnetic force, magnetic field problems. Now we're going to move on and take a look at, it looks like we have another problem with an AC circuit. This is pretty similar, isn't it? Let's take a look at problem 3. This is kind of similar to the one that we just looked at. So make sure you're looking at other examples from chapter 30. Not just the AC circuits, but you're also looking at DC power supplies. And then there's also some oscillating circuits in there that have no power supplies at all. So those are also, take a look at the homework problems from those. But in problem 3, the one at hand here, what we have is we've got our AC power supply. This time we just have a resistor and an inductor. Now again, this is kind of a standard electric outlet operating at 60 hertz and 120 volts. And of course, the hertz for us is not standard units. We want to get that converted to radians per second, which is going to be 377. The resistance is given. We're told the resistance is 765 ohms. That's a lot of inductance. So we have 2.50 henries of inductance. It's good to say henries. And so how much reactance is that? That's 943 ohms. So I think we're answering these right. Calculate the reactance and the impedance. That's the reactance in the inductor. The overall impedance, R squared plus XL squared square root, is 1214. Now in this case we're not getting any cancellation because there's not a capacitor. So I'm getting this much of an effect from the inductor, and then at a 90-degree phase relative to that, we're getting a resistance, and that means that the Z is going to be calculated using Pythagorean's theorem, which is the formula that we used right here. So we've got the impedance determined. What we also have, did B ask about the angle? Draw a phase diagram. And I threw the angle in. It didn't specifically ask for it, but it seemed like a good thing to do. Let's see if I did any better job scaling here. Yeah, the scaling looks pretty good. So R needs to represent 765 ohms. XL needs to represent 943. I made XL a little bigger than R. Okay, so that's a pretty good diagram. And then the angle, the phase angle. Okay, I changed the notation here. I probably should go back and change that too. So here I used theta, but here I used phi. Sorry about that. But those angles, they are the same thing. So let's get that question answered right now. And then finally it just says how much current will we have operating. Well, if the VRMS is 120 volts, and we divide through by the total impedance, that's going to give us about 100 milliamps. Now don't say about 100, leave it as 98.8. I get to call that about 100, but make sure that you're keeping 3 significant figures. Don't just round things down, don't round things. Keep the 3 sig figs throughout. Questions on that? All right, all good examples. I like all these problems. All right, let's move on to this last one. So the last one is saying that we have, well, there's an intensity of sunlight that reaches planet Earth. The sunlight reaching planet Earth has an intensity of 1350 watts per square meter. That's how intense sunlight is at the location of planet Earth. So what they want us to do is just take that sunlight and calculate values for the RMS E field and the RMS B field for the light, and then they say energy density, what's the net force of the sunlight on a perfectly absorbing surface. It says it's a roof, assuming that the light impacts directly perpendicular. So if we have a direct hit of the sunlight landing, you know, maybe the roof is tipped so that the sunlight coming in hits perpendicularly. So let's go through. When we say intensities, remember the default is to use the average values. And so there is this, well, not really much in terms of fluctuation because sunlight coming in is, the phase on that is so random. And so, but we can think of that as an average value, 1350 watts per square meter. We're just going to run through those formulas that we learned in chapter 31. So again, in chapter 31, we took a little bit of a different approach just in terms of the formulas and their derivations. So in the textbook, they end up with formulas for the electric field energies and the magnetic field energies that look quite different. But here we've tried to unify it, and you're welcome to use either approach. But using the approach that we introduced in class, the energy density we can calculate as intensity divided by C. So we've gone through and derived these, and that gives us 4.50 10 to the minus 6 joules per cubic meter. So here is this sunlight coming in, and if you stand out on a nice sunny day, you can feel the effects of that, I guess. You can feel that energy showing up, getting absorbed. The energy density, the amount of energy in sunlight reaching Earth in a cubic meter is only 4.5 millionths of a joule per cubic meter. So, if somebody asks you, hey, how much energy is there in a cubic meter of sunlight? And a cubic meter of sunlight has 4.5 millionths of a joule. That's it, 4.5 millionths of a joule. But they're coming in at such a high speed. So it's just one of these cubic meters after another. 300 million of these cubic meters coming in every second. And so, a fairly low energy density, but a really large intensity. Now, the electric, or the energy densities for the electric and the magnetic field are each half of the total. So the energy densities then are half of this, 2.25 10 to the minus 6. And then what we can do is we can use the formulas for electric field energy density to get us an ERMS. Now remember, we started with average values. Those are the defaults when we're doing a problem. And so the defaults for the fields will be their RMS values, kind of the average values. The average value for an electric field in sunlight is 713 newtons per coulomb. The average energy density the average field value for the magnetic field, also 713. So if I write it as ERMS and C times BRMS, those are both going to be the same value, same units. Ideally, that's how we would define magnetic fields. Unfortunately, we haven't done that. So we treat magnetic fields in different units, and we divide through by a factor of C. And so to get the magnetic field in Tesla, we divide through by C, and that artificially suggests to us the magnetic field is a much smaller number than the electric field, but that's not really the best way of thinking about it. Side-by-side comparison, working in the same units, we need to put that factor of C back in, and that reminds us that there's just as much energy stored in the magnetic field components as in the electric field components for these propagating electric and magnetic fields. So, what were we trying to solve here? The fields, yeah. So we got the electric field RMS value and the B field RMS value both in Tesla and in newtons per coulomb. And then for part B, the energy density, well, we calculated that along the way. So I can just write that down. 4.50 10 to the minus 6 joules per cubic meter. How much energy is in a cubic meter of sunlight? 4.5 times 10 to the minus 6 joules. So 4.5 millionths of a joule. What about C is the net force on a perfectly absorbing roof? So you can see there's kind of a pattern here as to what questions I like to ask. So here is the area of that roof, 150 square meters. And remember, we've built the roof so that the sunlight can come in directly, or it's the time of year where the sun is coming in directly. Maybe these are solar panels and we want them to be absorbing, tip them during the seasons to... So the force is dp/dt. It's the rate of momentum being absorbed. And again, we're going to borrow that very same formula from special relativity, where momentum and the energy of light are related simply by a factor of c. So the force then can be given as 1 over c du dt, where u is the energy of the sunlight. Energy per time is power, and power is intensity times area. So the rate at which energy is coming in is at 200,000 watts. So that's a roof. If solar panels were somehow 100% efficient, we would be able to generate a lot more energy from solar panels, right? Yeah, so solar panels are just a fraction of this, like, I don't know, somewhere between what, 5 and 10, 5% maybe? Somebody can correct me on that number. Not that we shouldn't go the solar panel route. The solar panel route's a good route to go. We just have to build more of them and work at making them more efficient. And then if we take the power divided by C, so 675 micronewtons of force. So kind of similar to what we saw in that other practice exam. Not an enormous amount of force here. All right, that takes us through this example, the midterm sampler. Again, any questions that you guys have at all, stop by. We're completely in review and prep mode for the upcoming midterm. So stop by and we'll get whatever questions you guys have. We will get those looked at.